Thanks a lot for inviting me, and I'm really excited to be here. A little bit of my background: I'm working for a company called ABB, and I've been working here in now 21 years or so. All the time has been with marine vessels, basically. Before that, I was working for Kongsberg. All my professional career has been with vessels. I live in Norway. Come from Norway, and the last 10 years has really been about introducing this DC systems. It was a slow start, I have to admit. We developed it, or we launched it 2011, and then and not only us, there were also other competitors doing the same thing. So it was kind of DC systems were launched at 2011 and 12 from 2-3 companies, and one of them was ABB. And then it's been developed since then. It was mainly developed for offshore market, and as you probably all know, it kind of collapsed dramatically in 2013-14. So it was a slow start, but it's gained traction the last 5 years, and we see almost all the quotes we are now working with, let's say 80%, is really looking into also DC systems. But I'll come back to that. So did we agree then? We will have the questions for later after I went through the slides, maybe?
Yeah, that'll be fine.
Yeah, okay. So then just note them down as we go, and we take them afterwards. Yes, so the agenda I put together today was really not too technical down to how things are working, but really more on try to give an insight on why we have seen this shift and more of these DC-based systems, and why it makes sense, and also when it brings value. And now, especially with the DC-based energy storage systems and also fuel cells and other stuff, I'll come back to that. And also there are clear boundaries for these systems. It's based not on ABB, but in general, the level of voltage and power level are limited. So there are kind of some limitation on the vessel types it will fit. So that's also useful to know. Okay, so then I'll jump right into it. And now, slide was supposed to work. Yes, yeah. So as I said, it was launched now more than 10 years ago, and it was mainly for the introduction, or we said reclaiming variable speed of combustion engine. So before the electrical propulsion came along in the 80s, 90s, then we had this mechanic on many vessels, and we still have, but there are vessels that switch to this electric, and then doing it with AC-based systems, and then you have a fixed speed setup. They are fixed to the 60 or 50 hertz, so you cannot adjust them. But with the DC, you can freely control each individual combustion engine speed. So that gave a tremendous saving and better combustion efficiency. So that was the main reason at that time. Later, it's been showing that the introduction of battery systems is really much easier to integrate on DC-based system, basically because they are DC-based, and same goes for fuel cells. And also not only the physical component needed, I will come back to the details, but also the controllability of these sources is easier with a DC-based distribution system. So a little bit then on the concept itself. Probably many of you already know, but I kind of need to touch it, I think. So the basis of a DC grid or DC-based system comes from a frequency converter technology, and it's not a new technology as such. It is based on a multi-drive setup, the lower one. So basically, in the 80s, 90s, we introduced this, and we have basically taken that component and introduced some more protection schemes in order to act as a switchboard, but also software, embedded software for controlling the load flow and so on. But the technology as such is not that new. It's from the 80s and 90s. So that's what we are using as a base. And then here I will show you how it kind of works. So here you see a traditional AC system and a diesel electric with the alternators. Let me, is it a laser pointer or something? Here we go. Yeah. So the combustion engine on the generators is here, and they are now. This is an AC system, how it looks, and very on many of the vessels we are looking at is diesel electric propulsion. So typically 80% of the consumption of a vessel is going to propulsion through a frequency converter like this. So it goes to the switchboard, it goes to the transformer, down to the rectifier, and then the inverter. This is for everyone. This is how it works. So, and with a DC, we basically remove the transformers, these units, and we take the rectifier out and we rectify at the input, and then it looks like this. So it's the same, exactly same generator. The alternator is same, but we rectify before we distribute. So then you're not fixed to 60 or 50 hertz anymore, and in each of these sources can then be individually controlled on the speed and load, which makes the combustion efficiency better. And then we distribute on DC, so it's still inside the switchboard, and then out to the loads is now the inverter is then moved from the field into the switchboard, and then out to the motors. For the hotel loads, you would need still some AC loads, this 20% that's not frequency converter driven. Then we set up what we call off-grid, which creates AC network, which can feed the rest of the vessel, or a hotel load and pumps and so on. Right. So I'll touch a little bit more on this. This is also showing this kind of the same picture, but a real case. This is it's more on component level for a 63-meter yacht. That's electrical propulsion, and this is the AC system. So here you have the medium voltage, the low voltage switchboard here, the generator sets with the machine, ice, and then the alternator. In this case, we had a battery or two batteries, and for the battery you would need a converter and a transformer before it goes into the switchboard. And that's where you save space and equipment, because this is DC based and this is AC based, so you need a converter. And then you have the propulsion converters down to the propulsor. And then here is a tunnel thruster as well. So this is an AC system. This is typically the switchboard room. On a DC setup, it would look like this. So we move all the distributed converters, which is there today. The transformer is removed, and we move them in the switchboard. So now the main switchboard becomes switchboard and also converter. So the battery is a DC cable going directly into the switchboard, and then it's converted here inside. There's no separate unit to do that, and no transformers either. Same goes for the tunnel thruster and the propulsion transformer and drives. So typically for design perspective, the distributed converters and transformers are removed. The converters are then moved into the switchboard. So switchboard room is increased a little bit in size, but the total space is much less, or very often much less. So now there's a centralized DC switchboard with the converters inside. So it's still the same alternator, still the same electrical motor out here, AC, all of them, and AC cable as well, but it's now DC distribution in the switchboard. Yeah, since we don't have question now, I will continue, but I hope that's okay, and I hope it was clear. So then a little bit about why this is making sense, and this is highly dependent on the vessel type and if there's a big battery, small battery, not at all, and so forth. I'll show a few cases. But typically, the footprint reduction can be significant. It can be up to 50, it can even be more. I have a case with a ROPAX all-electric ferry, and then we are talking more than that even. But it can also be 0, so it really depends. So it's a case-by-case driven. So footprint and weight is one of the main contributors to seeing this nowadays. The other one is the variable speed on the combustion engines. So you can have much more or better efficiency on the combustion engine, specifically at low, or especially at low load. And then how you integrate batteries, it's much more efficient. And especially for road ferries in Norway, as you may know, there's a lot of these vessels with all battery driven, and the onboard efficiency from the charging plug to the propulsion can be as high as 92%. So you lose about 8 on the way. If that would be an AC, it would be much higher because of the conversion and so on. I'll come back to the details on that as well. What else here? No, I think that's enough. Yeah, it sums up the same thing. And the capex is less because you have less equipment, and reliable. It is still a multi-drive, which we have thousands of them already in marine around. And then, of course, the OPEX because of the reduced fuel consumption and better efficiency. Then a few cases I wanted to show you on. I took 2 cases, maybe one extreme one, the ROPAX one. Then we basically, with a customer, we sat down, we compared, took 2 real cases. One is the yacht, the other one is a ROPAX, all electric. And we made an AC setup, and we made a DC setup. And then we compared the relative volume, weight, and length of equipment, just to have some numbers. And here is a summary of that. So the one to the left is the yacht. This is a 63-meter super yacht, where you see the blue is the DC system, the red is the AC system, electrical propulsion, of course. So here you see not that much saving. You can see the length of equipment is reduced by 18%, and the volume is 35, and the weight is 38. And this is mainly because we remove transformers and we integrate battery more efficiently. And then, of course, the extreme case, which I'm almost a bit embarrassed to show because it doesn't seem to be true, but it's a lot of savings there. But this is a special vessel with all electric battery, but that's where it really fits well. So I wanted to show it. Here you see the component length is reduced by, in this particular case, a big vessel, 34 meters of switchboard and transformers, of 57% of equipment in length. And the volume was, even more, 77%. Again, much due to the transformers, but also in this case, the charging is medium voltage. But with DC, we can charge more because we don't have reactive current, so we can charge more on the same plug. So we manage without the charging or the transformer for the medium voltage. So it's an extreme case. It's not normal, but there are cases like this as well. And then it really makes sense. This is all electric ferry, and it goes for many of these. At least what I've seen out there now in the last couple of years, on these kind of vessels, there's only talking about DC systems, even the bigger one, because it makes sense. Both the efficiency, but also the equipment and capex. I'm sure you have questions, but normally I have them on the way, but let's keep them at the end. Now, some questions I always get is about the efficiency, the component efficiency. So here I just wanted to show because we do introduce some losses which you don't have in AC. So here it's just showing the DC on the left side and AC system on the right. So here you have the alternator. We need the rectifier, which have a 0.5% loss. Are you able to hear me, Jonathan? I think you're muted. Ah.
Sorry,
Okay.
I was trying to stop you getting feedback. Not a problem. Sorry.
Okay. Yeah. So then you can see some. So this is a added loss, electrical loss that we don't have on AC, and then we also have on the AC grid where you have your hotel load. Then we have more losses because we also there need an inverter to create the AC and the filter and then the transformer. On AC you only have the transformer. So then there's more losses there as well. So in the cases where you have most of your load going to your hotel, then it doesn't make sense in terms of efficiency. But if most of your energy goes to propulsion or you have a battery, then it's a completely different manner. So if you see here, then you have, I think it's stated here as well, from diesel generator terminals to shaft of the generator, no, of the motor, it's an DC is 97.9 and AC is 95. So this, because we don't need a rectifier, we don't need a transformer like here. Again, so that again depends on what kind of vessel you have. But all in all, it tend to make sense in efficiency. Right, so a little bit on the variable speed of the combustion engines. On the right side, you see, I think this is a Caterpillar engine, one of the first vessels we delivered. So this is showing the speed on the x-axis here, and the SFOC or the SFOC is in here. So the SFOC is the curves going here. So if you're running, and this is the load on the Y. So if you're running up at full load on a fixed speed, you're stuck to this 1800, for instance. In this case, it's 1800 RPM. So always running at that one. So at full speed, at full load, you don't see much savings on DC or variable speed. But the point with variable speed is that as you go down on load, so down towards this area, on AC, you're fixed to this speed. So you will move from typically up here, it's 200 grams per kilowatt hours output, and then it goes up. So all the way down here, it's much more, 240 and so forth. With DC, we will also, as we go down on load, we will also move down in this direction. So we will follow the curve and have higher, better combustion and efficiency. So typically at this load, for instance, what would that be? Like 30% load or something? We would have 212 grams per kilowatt hours on variable speed. On fixed, you would have, I think, 307 seems a bit much, but it's anyway much higher. And it again also depends on the machine. But this is important. So it's a dynamic control that always online controls and optimize the speed versus the load of the machine. And yeah. So I'll just continue. So how are we on time? We have time. Yes. Okay. And then when are we using and when are we seeing this? This is not only kind of ABB, it's also looking at the market in general, where we see the DC coming up now the last, let's say, 3-4 years. So this is just showing the percentage of the vessels with DC grid and DC systems. So you can see it's a mix of vessel types. We have Ropax and Ruro. We have yacht and cruise vessels, small cruise, OSV and OCVs, wind turbine installation vessels, even up to 30 megawatt installed. Tugs as well, introducing batteries, and of course, where it really makes sense is, as I mentioned, the car ferries, the road ferries, where you can use battery. or some of them. So among the DC grid system out there now, I think it's around 80% of them have an energy storage on board. So that's of course also a driver for this. Shaft generators are on some, and fuel cells are slightly small coming, but not many. There are more like pilot projects here and there. But this shows that it's a pretty wide range of vessel types. And then a little bit on the limits. This is quite, I wanted to highlight on where are we? And this is of course showing ABB as such, but it's kind of the same for others. Here you see the power sources is limited to 6 megawatt-ish. 5, 8, 6 megawatt is the maximum generator size you can have on this kind of systems. So there are vessels that this is not enough. It will cover a lot, but 6 is, and this is due to cabling. It's due to the low voltage, the current rating, and so on. So to have more than that is just unpractical. And then we need to get new technology. It will come in a few years, maybe 5 years. We are working on medium voltage DC systems, but not yet. So now this is kind of a limit. And this also goes for propulsion or single motors. 6 megawatt is the same limit. If it's bigger than that, the cable sizes and so on is really not feasible. Then we have charging, and then of course with DC you can have medium voltage, you can have low voltage charging, and you can have DC charging. And that DC charging tend to be more efficient, but it's also it's not that interoperability between vendors and so on. So the standards are not really there. So but if you need charging more than 3 megawatt, 3.5, then you tend to go up to medium voltage. Right, so that's also a limit. And then for energy storage, then there's 2 ways of that to introduce on DC based. You can do it on the, maybe it's too much details here, but it's through a DC-DC converter, like shown here. There's a converter to control the flow of energy in and out of the battery. But it also comes with it's called a direct online. It means that you connect the battery directly to the grid. And you can do that, but then of course controllability and so on is less, but equipment is less and efficiency is higher. So the bigger battery you have on board, the more sense it makes. Fuel cell is coming. Double FEV for DP2, where you have a system that you need redundancy, and even though you lose one side, it will still operate from the other side. And then of course the total installed power on the vessel. It's also a little bit of the practical cabling and so on. I would say we have there are vessels with 28 megawatt installed power, total installed power. But as you go higher than that, it's not really feasible, I would say. And the gains are lost because of the cables and so on. So then instead of DC, then you go to AC medium voltage. As long as we don't have DC medium voltage. There are companies working with it. Among them is us, but there's nothing on the market as far as I know for now. It will probably come. Right. So this is kind of showing the same thing. If you have, this is just trying to put the like a single line approach to it. This is a system where you don't really have electrical propulsion. You just have a plant with AC loads, like for instance, a LNG tanker. Then forget it. It doesn't make sense, DC, at all. Then if you start having a more complex system, now still without the battery, but you have electrical propulsion, it starts to make sense. But then it's all about small details here and there, if it's enough, and how the vessel is operated. If it's operated at full speed, more or less all the time, and you don't need variable speed, then maybe not a smart idea. But if you need it, then or if you have a variable operational profile like an OSV, then it starts to make sense. But it's still on the limit, I would say. And then if you start to have a battery like this case, then it really pays off and add value. And then in terms of size, variable speed, footprint, as I showed you, and also how you use the battery is easier. And then it goes even more complex if you have a shaft generator. It's also the same thing. You don't in a shaft generator on AC, you need a rectifier and an active rectifier to get to 60 Hertz. Here you only need one part of it because it's DC. Yeah, but it's all so basically, to sum it up, electrical propulsion. I think it starts to make sense. If you introduce batteries or other alternative sources, it's even more. Okay, so then a little bit on the solution as such, and this is showing the multi-drive or the switchboard. It's a 2 meter high, and this is very important. We see for smaller vessels where we don't have 2 meter high availability, the actual switchboard is 2 meter. So we need, and it's not only ABB, typically it's 2 meter plus this converters. And this is a problem in some vessels where the height is not 2 meters. and then in addition, you would need some cable entrance. That can be, of course, going from the room below, but still on the deck below. But it's a 2 meter high, typically on this power level. There are some solutions out there with the lower height, 1.8, but then, of course, the power levels are less. Okay, and then how you can, this is something I always discuss with the designers, how you put them in the vessel. So there are many ways to form them. You have the straight line up, you have the back-to-back. You can have L shapes and you can have U shapes. And that's all about how it fits in the vessel. And there's also, I didn't mention that, there's a cooling circuit, internal cooling circuit on all of them. It's a multi-drive, so there's a freshwater cooling circuit inside, and it connects to the freshwater circuit of the vessel. So you need, of course, piping and the freshwater cooling. Okay, then actually I have more details, but I believe it's more than how things are working. And I'm not sure we should go that deep. I really don't know. I can say a few words about protection because the DC protection is very, very different than on AC system. Short circuits are behaving completely different, much faster. So the whole protection philosophy is different and needs to be taken serious. And it's not typically, if you are into this, you would know time selectivity is what is used on AC typically. This wouldn't work here because the short circuit is in the range of few milliseconds, very few milliseconds, sub-milliseconds, instead of typically 15 to 30 milliseconds. So breakers, standard breakers will not work. They are too slow. So that's why there's been developed like new protection devices, static switches, they are called, where they act much quicker and microsecond level and makes the system redundant and also safe. So these are, it's a big topic really. Yeah, maybe this is not the place to dig too deep into it, but if there are questions, I'm more than happy to try to answer them. But this is important, and the same goes for battery. The short circuit levels of those are tremendously high when you parallel them, and this is also things that you really need to take care of, and that applies for both AC and DC. Yeah, this is now how more detail how it looks on a DC system.